Hello everyone, welcome to Conf42. My name is Imran and I'm a senior network lead. Today I'm presenting infrastructure as code for enterprise network and I will be focusing on automating SD-WAN and zero trust architecture. This session is drawn from real world implementation across example site like nuclear, solar, wind and enterprise data center as they are managing thousands of network devices. Let's start journey for today's session and I will be covering three main areas today. First, why traditional networking is broken and costing companies money. Second, how infrastructure as code fixes this problem with real examples from production environment. And third, I will be giving 5 practical steps to follow for your infrastructure. So let's begin. Let's begin our journey with the problem. We will be discussing the problem first, then the solution. The traditional network management is fundamentally broken at enterprise scale. Imagine, for example, we have 500 network devices and a security patch need to deploy across all of them. What traditional approach required? SSH into each device, copy the configuration, paste, and repeat this 500 times. This is going to take a week or more than a month. And one typo, you have to start it over. So let me tell you what happened in reality. Configuration shift silently, destroy network reliability, and device drivers from their intended state over time and making troubleshooting nearly impossible for engineers. And changes that should be taking a minute actually takes day due to manual coordination, change approval, and implementation windows. And when things break, there is no quick rollback capability. You stuck undoing these changes and restoring from outdated backup. So what industry demand? Meanwhile, business demand totally opposite. Business demand deploy the network changes globally in a minute, not day, and maintain the zero security gap with consistent policy enforcement and provide seamless connectivity across on-premises and multi-cloud environment. And this gap between the current capability and business requirement, it's what we are going to address in today. Let's focus on the solution. The infrastructure as code fundamentally changed the network management. So instead of configuring device manually, you write a code that defines your desired network state. And instead of hoping change work correctly, you test them automatically before the deployment in the production. And instead of manual fixes when problem occur, you deploy the correction with one click. And this approach based on four core principles. I will be explaining one by one. The first is declarative configuration. You define what you want network to look like, and the system determine how to achieve that state. Second, version control. Every change is tracked in Git. Why? To provide a complete history and one command rollback capability. Third, automated validation. Error are caught before the production deployment, not after the customer are getting impacted. You might be having thousands of employees at your site. Four, continuous deployment. From code commit to production deployment, it should happen automatically with zero manual step. So in our environment, managing over 500 sites, what previously it took 3 days, 5 days, a week, now it's complete in 15 minutes with 95% rate of success rate. Let's discuss the SD-WAN architecture. Let me explain how this works with SD-WAN using Cisco Webtainer. Webtainer is a vendor. I will be taking example of Webtainer as an example for better explanation. So the architecture, this architect had three main components. vManage, vSmart, and vEdge router. vManage serves as a centralized brain, which is handling the policy orchestration and configuration management. And what vSmart does, vSmart act as a control plane, making a routing decision and managing the overlay network. And vEdge router, we deploy at every site as a data plane. And vEdge router help executing the policy and forwarding the traffic. So the key advantage here is centralization. What it means, when you change a policy, Once in a vManage, it's automatically updated thousands of edge router, and your engineer don't need to do a SSH session. No copy paste is required. No engineer intervention is required. And when we are onboarding a new site, the entire network configuration, including routing, security policy, and monitoring, it's deployed automatically in a minute instead of several days. Declarative config. Here the transformation are in practice. What traditional approach says, 500 line of CLI command, which may be error prone, fragile, and inconsistent. And modern approach says, one YAML template, which should be version control and reusable across all websites. And the process, and this process has three main steps. Step one, define the template for each site type. Let's say we have a nuclear site, so we should be having a template for nuclear site with strict security requirement. And for solar site, which have a SCADA system, it should be isolated. And wind site with remote monitoring specification. Step 2. Store everything in a gate. In gate. Every modification from your engineer, you should logged in with the explanation. And change required pull requests which should be reviewed by your senior management or higher level of engineer. Step 3. CI/CD pipeline. This handles the deployment automatically. Syntax validation run first, security compliance check execute next. And if validation passes, deployment process to the target devices via API call. And let's say if anything fails, this deployment should stop immediately. The result, deployment that took several days, now it's completing in few minutes. So how GitHub workflow implementation works? So here how a real network change flow through the system. And there are several steps I will be explaining one by one. Step 1, the pull request creation. This should be mandatory. An engineer need to add a new VLAN, for example, at any site. So instead of logging into a router and they should create a branch in Git, edit the YAML configuration, and commit the changes with descriptive message. And an engineer should be having a open pull request. Step 2. Step 2 is automated testing trigger. Okay. So YAML check the syntax and policy compliance should be validated by engineer to ensure the change meet the security standard. And simulation testing should be deployed there in a virtual environment, which should mirror exactly same as your production environment. And all test results should be posted as a comment in the pull request. Step 3, peer review. Senior engineer should examine the business justification, security requirement, implementation approach. In reality, this validation catches the logical and design issue that automation might be missing in. Step 4, CAN deployment. This begin after the approval. Change deploy to 1 or 2 test site first, and the system monitor for 30 to 60 minutes. And if metrics look good, deployment continue. It goes by phases: 10%, then 50%, then 100% of that site. And let's say if anything fails, allow to stop and automated rollback restore the previous state of the configuration. Step 5, production deployment with the continuous monitoring. Why? Let me explain you why. First, real-time dashboard should be there to track the progress, and health checks should run continuously, because if anomaly trigger, we should be having immediate alert in our monitoring system. And this workflow really transform the operation from 3 to 5 days of change cycle with higher rate to same day automation deployment with 95% of success rate. Let's move ahead and move to interesting topic of this session, zero trust. Zero trust security represents a fundamental shift in network security thinking. I will be explaining why. So the old model said trust but verify. Zero trust says never trust, always verify. And this based on three core principles. Principle one is verify explicitly. What it's mean? Authenticate and authorize every connection request regardless of source. In practice, this means every user, device, application must be getting authenticated before accessing any resources in your environment. Authentication required a strong method. The method like their authentication and certificate and authorization is continuous, not one time. Principle 2. Least privilege access. Grant only the minimum required network access for each workload. For example, a SCADA system at Winside, which only communicate with the specific control server, and it has no access to corporate email, HR database, and unrelated to the system. And zero trust enforce this through policies. Principle 3. Assume breaches. Design security control assuming that attackers are already inside your network. This means segmenting your network so compromising one device doesn't enable lateral movement to other. And encrypt all devices, including internal traffic, and monitor continuously and detect the anomaly. Why? Because in environment, if let's say example for Winside, if device got compromised, the attacker cannot reach to corporate system at all or other sides of your infrastructure because each site should exist in own isolated security zone. Microsegmentation. Microsegmentation makes zero trust operation at a scale level. And I will be giving four real world example from the production deployment. First, consider the SCADA system. SCADA system is isolated. Example, we have a wind turbine, sonar inverter, which control are completely isolated from your corporate network. SCADA devices communicate only with the authorized control server, have no internal access, and cannot reach to corporate email or file share. Even if attacker compromise a corporate network, they cannot reach to SCADA system. Second, application segmentation. Where tiers are separated from application and presentation layer. Web server cannot directly access the database. It's only able to access through approved APIs. Third, user context-based policy. Access change based on user identity. Device compliance status, location, and time also. Let's say, for example, an engineer accessing SCADA from corporate network during business hour on a managed device which are allowed to the network. But when same engineer from the public Wi-Fi at night time on a personal laptop, it should get denied and it should require a additional authentication. Fourth, traffic prioritization with quality of service. The mission critical SCADA traffic always get a priority, even during attacks, and voice traffic never suffer latency or a packet loss. So microsegmentation deliver both security and performance together. Routing protocol automation. Enterprise network run multiple routing protocols across different domains. In real world network, you will see BGP for internal edge and service provider connection, EIGRP or OSPF for campus and branch routing, and the OSPF for data center fabric routing. The problem is each protocol has different configuration, metrics, and behavior, right? So managing them manually across thousands of network devices might be error prone. So automation solves this through continuous protocol optimization. The system adjusts the routing metric based on real-time telemetry. Let's say if link experience high latency or a packet loss, it's automatically increase the cost so the traffic prefer the alternate path. Redistribution policy are optimized automatically to prevent the routing loop and suboptimal path. The path selection are based on application requirement. Voice traffic route over low latency fiber link, bulk data transfer use lower cost link only. Let's take a real example. Example Winside. At a Winside, at Winside running a BGP with ISP and OSP internally. So automation continuously monitor this link quality. When ISP link degraded, BGP automatically fail over to secondary ISP without any manual intervention of the engineer. And if internal OSPF link fail, the protocol reconverts in a second and we should be having immediate alert in a monitoring system. Let's move ahead and see the network data center networking, ACI fabric. The Cisco ACI represent a shift in a data center networking, and this based on three key pillars. The first is application-centric policy model. Traditional networking is device-centric, right? But you configure VLAN on switches, you require access lists on firewall and routing on router, but ACI is application-centric. You define the policy based on application requirement and ACI translate them into device configuration, which should be automatically. And you never configure any individual switch port. It should be automated. Second, spine leaf fabric architect. Every leaf switch connect to every spine switch in full mesh. If any leaf can communicate with any other leaf, it should be 2 hop maximum. This provides consistency, low latency, and high bandwidth. The VXLAN overlay, which enable a massive scale environment with many millions of endpoints and thousands of VLANs. Third, API-driven management. Everything is API-driven. The third pillar, API-driven management. So everything in ACI is API-driven. You can integrate Terraform, Ansible, and Python script. CI/CD pipeline automatically provision the network resources as a part of application deployment. And you can query the fabric for real-time health metrics, traffic flow, and policy compliance. ACI integrate with SD-WAN controller, and when you deploy an application in a data center, ACI provision the network and SD-WAN policy update automatically to allow the branch offices to access the application. And security policy are enforced consistently from branch and router to the data center core. Let's see how cloud integration work here. In modern enterprises, which using AWS, Azure, cloud network, and some of them may be having a private data center, and your network automation must suppose this reality. I will be explaining 3 key integration points. First, AWS integration. The AWS Transit Gateway connect multiple VPCs and on-premises network through a central hub. So instead of managing point-to-point VPN tunnel between every VPCs and every site, everything connect to Transit Gateway. And when deploy a new site with the SD-WAN router, it automatically establishes the VPN tunnel on AWS Transit Gateway. And the site instantly have access to cloud-hosted monitoring application without any manual configuration of VPNs. Second, Azure Cloud Connectivity. Azure Virtual WAN provide hub-to-spoke architect, means connecting multiple region on an on-premises site, and Azure automatically manage the routing between the spoke via hub. And automation script created in a virtual WAN connection. And when deploying a new site, so policy-based routing direct the traffic appropriately. Third, the policy consistent across all the environment. So this is the most critical benefit. The traditional setup configure on-premises net firewalls, AWS security group, Azure network security group separately. This lead to policy drift and security gap and compliance failure maybe. The solution is define the policy once in centralized engine, or automation translate them into a platform specific configuration. For example, SCADA system communication. The SCADA communicate only with the control server on port 502 and it's enforced identically on premises in AWS and in Azure. Monitoring play a crucial role. So automation without the monitoring, it's like we are walking blindfolded. You need a real-time visibility to detect the issue proactively. And this based on four key metrics. I will be explaining one by one. The first, interface utilization and the error rate. We collect, for example, I am taking example of our site. So we collect the interface statistic every 60 seconds. And if utilization exceeds 80%, the alert trigger, it should be. If error rate spike, incident ticket open automatically in our engineer support group. Second, application performance metric, which include packet loss and jitter. We continuously measure the latency between the site and the IP SLA probe and the net flow data. And if latency exceeds the threshold, we investigate routing path and the link quality. Third, security event correlation. Our SIEM ingest log from firewall, SD-WAN controller, and switch. Machine learning model detect the anomaly like a sudden traffic spike or a normal IP address, which should trigger the alert in monitoring system. Fourth, policy compliance validation. We continuously validating the device that run on approved configuration and security policy are consistently applying on it. If configuration drift occur, the alert trigger and automated remediation can be reapplied to the correct configuration. All telemetry fit into monitoring platform, providing end-to-end visibility from application layer to the physical infrastructure. When issues are detected, automated alerts are triggered in engineer queue and incident ticket are automatically with the help of runbook guide troubleshooting, it get addresses. And if the issue is known, automated remediation execute without the engineer intervention. Let me give the 5 takeaway from the today's session. And by following this, you also can implement the SD-WAN in your environment. So five actionable item steps you should follow to implement in your environment. Takeaway one, start the version control. So before automating anything, migrate the existing network configuration into a Git repository. Pick one device type, export the configuration and commit them into Git with meaningful folder structure. And establish a process where any configuration change must be committed to Git and this costs nothing to implement but benefits are immediate. Takeaway two, build a validation framework. Before deploying any changes, validate them automatically. Implement pre-deployment testing, including syntax checking, policy compliance checking, and simulation testing in virtual environment. And this validation really catches 80% of the error before going into production or before going to takeaway 3. Adopt gradual rollout with canary deployment. Never deploy changes to all devices simultaneously. Deploy one or two test devices first and then monitor for 30 to 60 minutes and then roll out to 10%, 50%, and then 100%. At each stage, automated health check which should be there, which validate the success. Gradual rollout limit that blurs the radius of failure. Takeaway 4. Integrate the monitoring earlier. Deploy comprehensive monitoring before the automation to establish the baseline metric. You need to know your network normal behavior before the automation changes to it. And automation is only safe when you can detect the issue immediately or instantly. Takeaway 5. Automated rollback procedure. Ensure automated rollback capability for rapid recovery from the failed alignment and maintain the previous configuration in Git so you can always revert to the last known good state of that configuration. And test the rollback procedure regularly before going into the production so that we won't be having any false incident. I must say, start small, pick one use case, prove value, and then only scale. This worked across more than 500 sites for us. You also do it too. So thank you so much for your time today. To recap, traditional networking is broken. Infrastructure as code fixes it. You can start today with your version control. The journey to automate policy-driven zero trust network infrastructure is achievable. So start small and then go for scale. I hope this session provided practical insight and actionable strategy for implementing infrastructure as code in your network environment. Thank you so much.